All right, welcome to physics. We are now in our third activity of texting and driving, and we're really going to be able to complete a full scenario and an entire scenario. So we're really getting through the background information that we need before we kind of start this big project. So our focus today is how far will the car travel while braking? So this is our distance while braking activity. So the next step in our texting and driving lab is calculating how far a vehicle will travel when the brakes are applied. We all know that hitting the brakes doesn't stop you instantly. Okay, there's a gradual stop. So we need to understand the factors that go into braking and what might change our braking distance. To start with this, I really want you to watch this video. I'm not going to do it in my little video here, but I want you to watch this because this will talk you through how do brakes work on a car. And honestly, I learned information from this video and found it incredibly interesting because we've all been in a car and we've all experienced braking, but actually understanding the physics behind it, maybe not so much. And so it's only 6 minutes. You only have to watch the first 6 minutes, and it'll talk you through some of the physics, but also show you some really cool examples of brakes over time. Then I have here a little reading for you. This is something I didn't want to have you get in a car and collect data um, about your braking times. Okay, that sounds a little dangerous. So for this activity, we're going to utilize some professional surveys that have been done. And so this one is from NACTO.org, which is the National Association of City Transportation Officials. So these are the people that study and make decisions around city transportation around the entire country. So what they have found is highway traffic and safety engineers have some general guidelines they have developed over the years and hold now as standards. As an example, if a street surface is dry, the average driver can safely decelerate an automobile or light truck with reasonably good tires at the rate of 4.572 meters per second per second. Okay, so in there's a couple pieces. One, a dry surface, okay, braking safely, and the weight of the vehicle, along with having good tires. Okay, if your tires are old and worn, then this will be different. Okay, so 4.572 meters per second per second. That's the rate of deceleration. So another way we could write that is a negative 4.572. Now, that is a driver can slow down at this rate without anticipated probability that control of the vehicle will be lost in the process. What that's saying is, if you decelerate at this rate, it's pretty much guaranteed that it's going to be a safe stop. Okay, your vehicle's not going to slide and get out of control. Continuing, under closed course conditions, okay, professional drivers frequently achieve what's called 1G deceleration. And 1G relates to the force of gravity. Okay. And so 1G deceleration would be a deceleration of 9.72 meters per second, which is pretty dang impressive, or better. So sometimes it can get slightly better. A reasonably skilled driver could easily get deceleration rates in excess of 6.1 meters per second without loss of control. It is very possible and probable that with some effort, the driver that attempts to be aware of braking safety and procedures and practices can and should get much better braking safely than the guidelines used nationally. So, kind of just an interesting bit of information there. When they're thinking about making rules and policies and speed limits, okay, when they think about the timing of a stoplight, that they are considering you braking at this deceleration rate. But they recognize that a lot of vehicles these days, or if you're a skilled driver and kind of alert and so forth, that you can decelerate at a better rate. So really, they're being overcautious in where they set this standard and build these laws and rules around. And based on our distraction and reaction time, that might go to kind of be a reason to why they might be overcautious with that deceleration rate. But yes, so this gives us an idea of what a normal deceleration, somewhere between 4 and 6 meters per second would be a relatively normal deceleration. Now, for question 1, I want you to check out this website to answer the following questions. The following question. So what factors below affect braking distance? So if I open this link, it's going to open this article here. And you're welcome to read this entire thing. But really, I want you to pull out the factors that affect braking distance. So if you just go through this quickly, you're going to see brakes, rolling resistance, and it gives you a little example of what this means. Air resistance, tires, starting speed, gradient, towing, and then continues to go on what some typical stopping distances might be on dry and wet roads. And we're actually going to see this same data a little bit later in the activity. But again, the factors are listed here and kind of explain them for you if you want to read those. So then you select which ones you just saw. Now we're going to practice calculating the distance traveled while braking. And kind of briefly, this is actually in the video here. So you can see the same distance equals half times initial velocity squared divided by acceleration. It's the same equation, and this guy goes through to explain it. And I'll go through some practice problems as well here. So this is the equation. Okay, a little more complicated than what we've worked on in the past, but really it's just putting it into your calculator correctly, and we just need to know two numbers. So in order to solve for distance traveled while braking, we need to know the initial velocity. And again, this is the velocity before the brakes are applied. That's what that's referring to. And then the acceleration, or in this case, since we're braking, we'll refer to it often as deceleration. And so that will be represented by the A value. Okay, so again, using that will give us our distance traveled while braking, or we're going to refer to it as dB, capital D, lowercase b. And so now let's go ahead and practice. So a vehicle is traveling at 25 meters per second. That would be our initial velocity. It sees a red light and gently hits the brakes, leading to a deceleration of negative 3.5 meters per second. Okay, so what is the distance traveled while braking? So we're going to go ahead and plug this in. And I'm going to use my cursor just because we don't have some of the symbols that we need. So dB equals 1/2. And when I put 1/2 into the calculator, I almost always write it as 0.5. Okay, it just for me it feels easier than using a fraction in the calculator. Okay, so just something to keep in mind. And then this little dot is a multiplication symbol. If you don't know that, whoops, multiplication symbol. So 1/2 times, and then our VI squared divided by the rate of deceleration or acceleration. So if I rewrite this with the numbers in there, our distance traveled while braking equals 0.5 times, and then we had 25 meters. Ooh, it's so hard to write with the cursor. Per second. And I'll put that in parentheses because that whole thing is getting squared. And then divided by our rate of acceleration, which was negative 3.5 meters per second per second. Okay, so if I put that into the calculator, one way I might do it is kind of break it apart. Depending on your calculator, sometimes it's hard to do the whole thing. So for me, I'm going to solve for 25 meters per second squared. And so that gets me an answer of 625. Okay, and sorry my lines are crooked, but then that's going to be divided by negative 3.5. Okay, so divided by negative 3.5. Okay, and that got me an answer of 178.5. So now I can take this answer and I need to multiply it by half, or 0.5. Okay, so if I try and rewrite some of this, I will take, scribble, dB equals 0.5 times 178.5, and that gets me 89.2. Actually, I would round it up to 3. 89.28 is what I got. So 89.3, and our answer is distance, so it'll be meters. So I'll get rid of that. And my final answer is right there. Okay, so again, we took our initial velocity divided by acceleration. So I plugged that in here. We had 25 squared, okay, 25 meters per second squared. And then we had a negative 3.5 meters per second per second. That got me an answer of 178.5. And then I multiplied that by 0.5, or half, to get my final answer. And so this is, again, the distance traveled while braking. And the units are really important. I keep seeing this common mistake. If I'm asking for a distance, then you need to make sure your units are a distance. Okay, so just meters would be appropriate. And then don't forget to type in your answer there. Okay, so then you have a couple more problems. So you have another one similar to what we just did up here. Then you have a vehicle is traveling 20 meters per second, sees a ball bounce in the road and very quickly reacts aggressively, hits the brakes, leading to a deceleration of -6, so a little bit more extreme. If the ball is 40 meters away, will the vehicle hit the ball? So this is actually asking you to calculate the distance traveled while braking, but instead of just giving me that number, it wants you to answer this question: will the vehicle hit the ball? Okay, so make sure you read that carefully, and uh, basically, if your answer is less than 40 meters, the vehicle will not hit the ball. If your answer for distance while braking is larger than 40, then it will go through the ball. It will hit the ball. And that leads us down to Desmos here. So now we're going to be looking at some data about braking on dry conditions versus wet conditions. And again, this was actually from this activity here. So this is a wet road data versus our dry road data. And so I used that and plugged it into Desmos. So our first question is, does the vehicle stop better on a dry road, which is going to be Y1 or the green data, or a wet road, which is Y2, purple data? So that'll make more sense as we open this. So go and click this link, and it's going to open up Desmos. So again, you have Y1 data and Y2 data, and one is green and one is purple. So the purple is your wet road, and your green is your dry road. And then across the x-axis, we have our initial velocity in meters per second, and then our braking distance is our y-axis here. So again, if I'm looking at the data specifically, these actually share the same values. So that's why they're directly above one another. So at 11.1 meters per second, on a dry road, it took 26 meters, but on a wet road, it took 30 meters to stop. So you can see that the braking is not quite as good on a wet road. And you can also see that the space between these dots is starting to get larger. So what I did, I took the differences. So I did 30 minus 26, and that gave me a difference of 4 between a wet and a dry road. Then I did the same for all of these data points, and I plugged them in here. So this is going to be our Y3, which are these numbers down here, or these data points. So going to some future questions, okay? Did it stop better on a dry or wet road? We should be able to answer that now. And then what happens to the stopping distance as you increase the initial velocity? So this is just based on your observation using a complete sentence. What do you notice happens to the stopping distance as you increase the velocity? Okay, you should be able to look at this trend and be able to describe that to me. Now, looking at the difference, as I started pointing out, looking at the difference between the dry road and wet road stopping distances, which is Y3. What kind of pattern do you see? You should be able to identify, is this a linear pattern or quadratic pattern? And really, this is the one I'm talking about here, this curved line, or an inverse pattern, or if there's no pattern at all. Then I want you to use that line that I just referred to. And how many meters further would the vehicle traveling 40 meters per second sorry, let me read this. How many meters further would a vehicle traveling 40 meters per second travel while braking on a wet surface compared to a dry surface? So thinking about that scenario, 40 meters per second is roughly 90 miles per hour. And if you had a vehicle on a dry road going 90 miles per hour and brake versus a wet road going 90 miles per hour and braking, what would be that difference? So the little hint here, drag your cursor along the quadratic pattern until you reach the velocity x, and then you want to record the distance here. So just to show you, again, you have this line, you can drag it, and again, your x and y values are always listed in a specific order. So x is always on the left, and then you have your y. But if I drag this to my velocity, that will get your answer. And you can also zoom out if you need to and go to that velocity. Okay, so you should be able to see that. And this, again, this is representing the difference between a wet road and a dry road following this pattern. So we can then talk about that, and you can put that in a complete sentence as well. All right, so now this is kind of like the finale of these three activities. And you're going to see that it's really a complete scenario. So let's review. So far, we've learned how to calculate the distance a car traveled while distracted, which is our distance equals velocity times time. Then we just finished a distance a car traveled while a driver reacted to hit the brakes. And then the distance a car traveled while braking is what we just did. So now we have this complete scenario. So using these three steps, can you determine this scenario? So the question is going to be, how far did the car travel while the driver was distracted to when it came to a complete stop? So again, really the entire scenario of being distracted, not seeing what's going on, and then reacting to something that they need to stop for, and then actually braking and coming to the stop. So scenario one, here it is. A driver is running late to work and decides to drive at 32 meters per second, which is about 70 miles per hour. That's above the speed limit, just for the record. So they're running late and they're going extra fast down the freeway while eating McDonald's for lunch because they're running late, right? So while eating, the driver accidentally drops a French fry to the floor. I have definitely done this. Okay. So the driver, though, decides to try and reach the fry, but in doing so, takes their eyes off the road for 5 seconds, just 5 seconds, not too long. I mean, they're reaching down, they're trying to get the French fry, and then they look back up. So when the driver's eyes get back to the road, they see that traffic in front of them, 235 meters away, has come to a complete stop. Now, in the real world, they wouldn't be able to know this, but in our scenario, we can kind of give you that information. So traffic now right in front of that driver is just stopped. Maybe there's an accident, maybe someone merged wrong, whatever. Maybe there's just too much traffic, so it comes to a stop. This happens a lot. And so the driver then takes half a second to react. By the time they pick their eyes up, they see it, and then they hit the brakes and decelerate at an incredible, remember, professional course was 9.7. So this is just under that at 8 meters per second per second. So this was quite fortunate that they could brake that hard at incredible 8 meters per second per second. So again, can we calculate this entire scenario? This is how we want to approach it. So we want to show our work, and we want to use these three calculations and then add them together. Okay, so we're going to solve for the distance while distracted. We're going to solve for the distance while the driver reacted, and then we're going to solve for the braking distance. So if I go into here again, I'm going to type, ooh, that's too big. Let's type this smaller. Okay, so this would be our distracted distance. Okay, distance equals velocity times time. Sorry, my brain is slowing down on me. Distance equals, okay, if I look at the velocity, it's 32 meters per second times how long were they distracted for? 5 seconds. Okay, so that is going to give you your value there. Okay, I'm not going to give it to you. I'm going to make you do it. Then you take your reaction distance, how far did the car travel in the half a second the driver was trying to react. So this is still d equals v times t. Hopefully that's convenient. Don't overthink that. It's the same equation. Whoops, if I could type. Okay, and then our velocity is still 32 meters per second because they haven't hit the brakes yet. So they're still getting to that point where they're trying to hit the brakes. And this was 0.5. Okay, and so that gives you that number. And maybe I'll do number 1, number 2, and then we have our braking distance. And again, this one's a little bit harder to write on the keyboard, but I will kind of paraphrase it a little bit. 0.5, as I said in the examples. Okay, and then you can multiply that by, and I will type this in because it's not going to work for me. So vi squared divided by acceleration. Oh, so much harder to type. Okay, so then this is really 0.5 times VI, again, oh, if I'm going backwards, 32 meters per second is our velocity squared divided by our rate of deceleration. Okay, is that -8? So then I can solve for this and get my distance while braking value, which will be our third number. So now we need to add for the total distance equals number 1 plus number 2. Whoops, these are the answers, right? The answer to problem 1, the answer to problem 2, number 3. If you add those up, that's going to be the total distance of this scenario. Okay, so again, be careful adding those into the calculator and then add them up, and you should be able to solve for this complete scenario. And when we feel good about that, we're going to be ready to really start creating our big project next time.